Hi everyone. In the previous classes, we discussed about resistors, dependent and independent sources, and we saw how to analyze circuits involving resistors and dependent sources in more intuitive and simpler forms. Now, in this lecture, we will analyze capacitors, and eventually, we want to analyze circuit comprising of resistors and capacitors using intuitions rather than solving equations and complex analysis. Okay, using complex analysis. So, first, I'll go with a simple brief definition of capacitor, and we'll just discuss a very simple capacitor circuits in this lecture. So, a capacitor. Uh, the fundamental difference between a capacitor and a resistor is that in a resistor, the potential difference between the two plates is maintained between the two terminals is maintained by a flow of charges. Okay, a capacitor, on the contrary, is a two-terminal device. It can maintain potential difference between the two plates by having fixed charges. There is no flow of charges here, but rather the charges are fixed, they are stationary. Now those charges, by separating the two charges with a certain distance and maintaining an electric field, therefore you will also have a potential difference between these two plates or terminals here. So here one thing we can, for a linear capacitor, it is noticed normally it is noticed that it happens that as you increase the potential drop, or if you add more and more charge onto this plate and hence negative charge on this plate, the potential difference is also proportional to the charge added onto these plates. Said otherwise, if I connect a voltage source of V volts across a capacitor of capacitance C, then it's going to transfer charges onto this plate. So we know that from basic electrostatics that these two are initially assuming the capacitance voltage is initially 0, these two are initially non-equipotential points. So therefore charge transfer will take place until these 2 points are of same potential. So it will deposit, the voltage source is going to deposit a charge of plus Q and minus Q. It's going to remove charges from this plate and add charges to this plate, and it's the charge it's going to deposit is usually proportional to the voltage applied. Okay, so as I said, if you can either deposit charge and develop a potential, or from the voltage can actually deposit charge on the capacitive plates. So in both cases the charge is proportional to the voltage. So normally for capacitors we draw the charge voltage graph. You draw charge as a function of voltage and it's a linear graph. Now since it's linear, we introduce a proportionality constant, and this term happens to be capacitance. Now for a linear capacitor, your C is independent of V. The capacitance is constant and is independent of voltage. For a nonlinear capacitance, it will also be a function of the voltage applied across it. So now we will analyze a little bit about series and parallel capacitors. So if I connect two capacitors in series and apply V volts across it, okay, if I apply V volts across it, then we know, as we discussed again, the charge transfer will take place from here and from here to here. So this will deposit a charge of plus Q on this plate and minus Q on this plate. Now what happens in between is that you would have positive, see these two plates are neutral initially, these two plates are neutral initially, these two plates, let me draw it here. So if I apply positive charges here, the negative charges on this plate would move to this point and this plate would become more positive. Okay, so but if you see, there is no potential drop across this wire because this wire is assumed to be a zero resistance wire, and even though there is charges separated there is no, it doesn't have any current, or there is no flow of once the charges are in static position, there is no flow of current. So therefore there won't be any voltage drop, there won't be any potential difference between these 2 points. They are at same potential. Okay, it's just that their arrangement of charges is different. Okay, so one thing you notice here is that the charges are all same. The charges on all the plates, of course the negative plates, it has negative polarity, the charge is same. So when two capacitors are in series, we can say that they will share the same charge. So they are like similar. As I said, the charge can be seen as a similar equivalent to current in a resistor. You need current to develop a potential drop across a resistor. Similarly, you need charge to maintain potential drop, a voltage difference between the two plates. And for series capacitors, the charge is same. Likewise, in a resistor, if two resistors are in series, the current is same. Both the resistors carry same current. So using that, we can simply say your Q is C1. Assume the voltage across the C1 capacitor is V1 and C2 capacitor is V2. C1 V1 will be equal to C2 V2, and also we use other result that V1 plus V2. KVL is still valid. It's an electrostatic circuit, so therefore KVL has to be valid. It's equal to V. So from this we can simply find V1 as C2 upon C1 plus C2 into V, and V2 as C1 by C1 plus C2 into V. Okay, so here you can observe that the charge is same for both the capacitors. Okay, so the larger capacitor will have a smaller voltage, and the smaller capacitor will have a larger voltage across it, because the charge has to be same. So that's what this result tells you. If C1 is greater than C2, then obviously V1 will be less than V2. V2 will be greater. Okay, so the larger capacitor will take smaller voltage, and the smaller capacitor will take the larger voltage. Now also we can treat this as a single capacitor. So if you can equate if you take one of these equations, you will get, if I replace in place of V1 I replace this equation, I will get C1 C2 by C1 plus C2 into V. Okay, now I can analyze this series capacitor as a single capacitor of value C1 C2 by C1 plus C2. The series capacitors C1 and C2 can be modeled as a single series capacitor of value C1 C2 by C1 plus C2. Okay, and again these are all well known results. I am just refreshing it before we go to analyzing bigger more complex circuits. So when two capacitors are in series, the charge they share will be same. Okay, the charge they all contain will be the same. So here I have already assumed that they don't have any initial charges across them. Okay, so the excitation or the voltage that I am applying is what that is providing the charge for both the capacitors. Now same way you can extend for n number of capacitors. The net, if they are in series, if n capacitors C1, C2 and so on till Cn, they are all in series, then we know the net capacitance is given by the C1 by C1 plus 1 by Cn. Okay, again this is very easily derived using what we just did, can be derived using what we did for two capacitors. So when two capacitors are in series, they share the small charge, same charge, and larger capacitors will tend to have smaller voltages across them when you are applying the same a large voltage across the series capacitors. Now we will go for two capacitors in parallel. So if I have two capacitors in parallel, then the voltage across them is same, but the charge will be different. They will carry different charge, and here the larger capacitor will contain larger charge. Okay, because the voltage is same for both of them. So the larger to maintain the same potential difference for a large capacitance, you need to inject more charge. So your Q will be larger. So if I assume Q1 will be C1V and Q2 will be C2V. So obviously if C1 is greater than C2, then your Q1 is greater than Q2. Okay, and in a very similar fashion, we can actually show that these two can be represented as a single capacitor of value C1 plus C2. Okay, so with the voltage is same, it can be analyzed as a single capacitor of value C1 plus C2. So we can see that, yeah, so because this total capacitor C1 plus C2 will demand a certain charge, which will be same as the individual, which will be sum of the two individual charges demanded by C1 and C2. What I mean by that is, if I apply a voltage source to two capacitors C1 and C2, you would have charges transferring to this plate and to this plate. Okay, and it is equivalent to a single capacitor of value. If I apply the voltage here, the charge transferred from a single capacitor of value C1 plus C2 will be same as this in this circuit. So these two circuits are equivalent to each other. So the total capacitance will be sum of all the capacitance. So similarly, when you put capacitors in parallel, the net capacitance will always add up. Assume I put n capacitors C1, C2 and Cn are in parallel, then the total capacitance will be sum of all the capacitors. Okay. So here larger capacitor will contain larger charge. So here the important point is the charge is different for all the capacitors, only voltage is same for all of them. So when capacitors are in parallel, you simply add them, and they are in series, then you find the equivalent using the C1 C2 by C1 plus C2 equivalent to that. the inverse, you add them with their inverse values. So this covers about the capacitor, parallel and series equivalents of capacitor. Now we are eventually going to use these capacitors in circuits, electric circuits. When we talk about electric circuits, we only talk about voltages and currents. We don't normally talk about charges, because when you are going to analyze a circuit, eventually your circuit will comprise of resistors, capacitors, voltage sources, and dependent and independent voltage sources. So we need a common terminology. So we only talk in terms of voltages and currents. So charge is normally not used in a circuit unless specifically we can talk about it, but we don't need to go for charges while analyzing RC circuits. Okay. So for that we again have to define voltages and currents in terms of voltages and currents. So we know your Q is simply C into V. So you differentiate this on both the sides, you will get dQ by dt is, now here I'll assume that the capacitance again is independent of voltage and time. So it will be C dV by dt. So this is your current. So the current through the capacitor is actually dependent upon the rate of change of voltage. Okay. It's not proportional to voltage like a resistor, but rather rate of change of voltage. So from this I can say the voltage across a capacitor can be written as 1 over C integral I of t dt, okay, minus infinity to t. Now normally we start your systems from 0. We normally start our systems from 0, time 0, and this value of integral minus infinity to 0, 1 by C I of t dt is what we call as an initial condition. I am going to call it V of 0. This is your V of t. So here there is a very important point to consider. We will analyze what happens. Let's say we start the system at 0, and I will also make another assumption that V of 0 is 0. Initially the voltage across the capacitor is 0. I am just starting the system at t equal to 0, and I am interested in finding out what happens at 0 plus, a very very small time after 0. I will call 0 plus as 0 plus epsilon. So your V of t will be 1 by C integral 0 to epsilon I of t dt. So now here I will make another assumption that epsilon is so small that your current waveform, whatever be the waveform value of the waveform shape, it's very very small in that interval 0 to C, it's nearly constant in the interval 0 to epsilon. I'll assume the value is I naught. Okay, it's nearly same, and the value is I naught because epsilon is so small that it's like a point value, it's same. So you get 0 to epsilon, which is nothing but I epsilon by C. This is your 0 plus. Okay, this is V of 0 plus. If epsilon tends to 0, V of 0 plus also tends to 0. Now what does this tell us is that for your capacitor, even though your current can be very large, you can inject a very large amount of current, you can transfer charges at very fast rate, you can transfer them at a very high rate, rate of change of charge is current. Still, as long as your I naught is finite, the change of voltage V naught of 0 plus is 0. Okay, so meaning your V naught of 0 plus, because epsilon is 0, it's very very small, you multiply it by a large number, it still gives you 0. So therefore your voltage across a capacitor cannot change instantaneously. That's what this equation tells us. The value of this equation, this comes from a simple integration principle. For any finite valued function, if you are going to integrate it for extremely negligibly small, infinitesimally small amounts of time, it will amount to nothing. Okay, as long as the function is a finite valued function. Okay, so that's what this equation tells us. But now we will consider what happens in a practical scenario. You can never have for the sudden changes in the capacitor voltages. It will take some finite time for changes to take place. Now assume that I am going to connect a capacitor of value capacitance C. I am going to connect V volts across this. Okay, this is V volt. I am going to connect it across this. Now I will suddenly close this switch at t equal to 0. At t equal to 0, the switch is suddenly closed. When the value of high here represents the switch is closed. Okay. Now as soon as you close the switch, this is an ideal voltage source. The voltage across the capacitor has to be V, right? The moment you close the switch, V of 0 plus has to be V, right? The instant you close it. Before your switch was closed, the capacitor voltage was 0. V of 0 was 0. The instant you switched it on, the capacitance voltage has to reach V. But as far as circuits is concerned, yes, this is going to happen, right, because it's an ideal voltage source. So then how does this happen? In that case, the current flowing will be infinity, okay, but since it's an ideal voltage source, it can actually provide that infinite current, okay. So I can see it. So what I'm trying to say is your voltage is actually integral of current, and as I said, if your integration time limits is very small, negligibly small, okay, then the value of the integral will always be 0. But if your current is an impulse, with meaning it can exist for no time, but its value of integration will be finite, then your capacitance can have a sudden change in voltage. So your capacitor, so I'm going to say something which is generally not true for practical circuits, but for ideal sources you can have a sudden change in voltage in a capacitor. Voltage across it can change suddenly, provided the current coming out of the voltage source has to be an impulse, okay. So you can also see it's C dV by dt. So the capacitor voltage is a step, then the derivative of a step function is an impulse. This is again a well known result. So if you differentiate a step, you get an impulse. So if I have an impulse of current, so you need an impulse of current for you to change the voltage across the capacitor suddenly, but okay, for a finite step value. So that's what this is. Also comes from the equation, also from intuition. Now when I say intuition, what exactly is happening here? The instant you connect this capacitor to this, the charge is transferred to this plate. So your current is simply dq by dt, okay, it's dq by dt. The current is dq by dt. When can your current be infinity? If in a finite amount of time, when dt is finite, but I'm going to transfer an infinite amount of charge, then your current can be infinity. The other possibility is I am going to transfer a finite amount of charge, but in no time, absolutely less time, absolutely no time, then your dq by dt becomes infinity. So that's what is happening in this case. You are transferring a finite charge of value q equals to cv, but then the charge transfer time is instantaneous. I mean it's instantaneously transferred, okay. So therefore your current will be an impulse, okay. There is no current. Once the moment is charge is transferred, it is static. There is no moment of charges afterwards, but instantly the charge transfer takes place. So the voltage will be a step across the capacitor of value V. So for charge transfer to happen instantaneously, or for the voltage to develop a step, you need to have an impulse of current. So that's the important point here, okay. So now we'll just analyze for different current inputs how does the capacitor voltage behave. So if I apply a current, an impulse of current, we saw that the voltage across the capacitor will be a step. It's just an integration of an impulse step. Now if I apply a step current, meaning I am going to increase my current as a step function, then your capacitor voltage will increase linearly. So this is C. Assume the I naught, the value of step current is I naught, then it will be I naught by C into T, okay. It will increase linearly, assuming the initial voltage is 0. Initial voltage across the capacitor is 0. If the capacitor already had some charge, initially it had some voltage V naught across it, then your voltage will increase from V naught. This will be V naught. So similarly, the direction of current is important. The direction is moving in this direction, okay. So therefore the voltage is increasing. If I reverse the direction of current, then the voltage will decrease, or if I apply a negative step, the voltage will decrease. So you can actually start from here. If it had an initial voltage of V naught across it, then it will cross here, okay. It will start from voltage and then linearly start reducing. Again, if I apply a ramp input, I'm not going to do that. If I apply a ramp current as an input, then you will get a parabolic voltage. The voltage will follow a parabolic shape. That's it. So these are the 3 points you need to know about capacitors. Later when we analyze a complex RC network, I'll use all these concepts, okay, all these ideas. So it's better that you just remember this. Now we will analyze it with voltage sources. What happens with a voltage source? So if I connect a voltage source and suddenly apply a step voltage of 0 to V volts across the capacitor, then we know the current flowing through the capacitor is an impulse, okay. So the current will be an impulse. So then meaning the charge is transferred instantaneously. Q here transferred is C into V. Now let's assume I have a 1 volt source. A capacitor is already charged to 1 volt. There is already charge present on this plate. There is 1 volt here. Now if I use a switch and instant at t equal to 0, instantly I connect it. Then these two are already equipotential surfaces to begin with. So there won't be any net charge transfer. There won't be any charge transfer at all. Okay. Now instead if I connect a 2 volt source instead of 1 volt, the capacitor is already charged to say 1 volt. Then when I short this switch, you will have a transfer of charge 2 minus 1, because these two potentials has to be equal. 2 minus 1 into C will be the charge that is transferred from voltage source to this point. So similarly, if I have a capacitor of 2 volts and you had capacitance, your initial capacitor was charged to minus 2 volts, then you need to completely, first you are actually having negative charges on this plate, you will have to completely invert it, you have to then make it positive. So totally you need to, the potential difference needed is 4 volts, 2 minus 2 is 4 into C. So that is the total charge that actually is transferred from the source. Okay. So in all these cases, the current is an impulse. The only difference is the impulse area will keep increasing. In this case, it's proportional to the charge. I mean, your impulse area of current is just the area under the impulse current wave, right? I mean, because your charge is simply integral of current. Okay. So the area under the current waveform will give you charge. So whichever circuit needs large charge will have a larger impulse value. Okay. So and also I've already defined how impulse function in the previous lectures, so you can go through that. So then you will understand what I'm saying. The area under the impulse tells you it gives you a magnitude of the strength of the impulse. Okay. So this is all about voltage waveforms and capacitors. So similarly, if I apply a ramp voltage across the capacitor, then the current will be a step. I'm not going to do it because we have already done it. Now if you apply a pulse input, so what I'm going to do is that I'm going to apply a 0 volt, 1 volt, and then eventually again it goes to 0. The input is going to 0 for a capacitor. Then what would be the flow of current? You will have a sudden transfer of charges at this point that will maintain 1 volt across it. At this point, let me use a different time. So this is say t. At this time, you will remove charges from the plate. So the direction of flow of current will be this. So your current will be negative. So it will be like two impulses of current, same impulses, and that will be your moment of current. And again, you can simply use c dv by dt to get the same results. I'm just telling you from intuitions. Okay. So this is how we have now defined capacitors in terms of voltages and currents. Okay. So now the next most important point is charge conservation. So in a capacitor, the charge is conserved, meaning it will never be lost, it will always remain same. So charge conservation is a very important principle, and in fact it will be very helpful in solving capacitive circuits. So say we have a capacitor of value C. I've initially charged it to say 1 volt, and then I'm going to connect it to another capacitance of value C after some time. The moment I connect it, these 2 points are not of same potential, therefore charge transfer will take place. Now the charge transfer will take place until the potentials are same across them. Okay, and again these 2 capacitors are in parallel, so the voltage will be, final voltage will be same. And as I told you before, parallel capacitances can be treated as sum of the 2 capacitors. So eventually I'll assume the capacitance is 2C, and we don't know what the voltage, final voltage is. Let's call it Vx. Whatever this, the steady state potential here comes to once the switch is closed, that should be equal to the initial charge across it, C into 1 volt. So therefore your Vx will be half a volt. So this is principle of charge conservation. Charge is always conserved. So and also you should remember energy is also conserved. Okay, in all these circuits energy is also conserved and charge is also conserved. So using charge conservation we can solve most of the problems. So for example, say you initially store 1 volt across this capacitor. So what I do here is at t equal to 0, I open this switch, I close this switch is closed, initially it is open, at t equal to 0 the switch is closed, and at t equal to 0 plus some t naught I am going to close this switch. So what will be the final voltage at this point or across the 3 capacitors for t greater than t naught? At a time here, what will be the final voltage? So first we'll assume these two switches are closed. First this switch is closed. So then you have a capacitor of C and C in parallel, which will have a voltage Vx developed across it. We just saw how to solve it. These two capacitors will charge share. This phenomenon is called charge sharing. The two capacitors will share the charge. Okay, the charge is fixed, and these both will start sharing the charges till their potential voltage drops are same. So you will have 2C into Vx will be equal to C into 1 volt. So your Vx is half a volt. We just derived it now, the previous problem. Now after some time, now I can treat this as a single capacitor of value 2C and half a volt across it. After some time, now we are going to connect it to another capacitance of value C. The moment we connect it to another capacitance, so first at this t less than t naught and greater than 0, t less than t naught and greater than 0, the voltage across the capacitor is going to be, the first capacitor is what I am asking, is going to be half a volt. Now finally, when I close this switch, the charge is still 2C into half, that's your charge. Eventually these two capacitors are in parallel, so you can treat them as a single capacitance of value 3C. Okay, so this should be equal to into Vx, whatever the final voltage it comes to, because these two potentials will eventually be equalized. So after charge is transferred, so that will be equal to 3C into Vx. So your Vx will be 1/3 of a volt. Okay, your Vx will be 1/3 volts. Okay, so this is how you solve these problems. Now here I'll just stop this lecture by just talking about one point, which is about energy conservation. Say we store 1 volt of charge across 1 volt of voltage across a capacitance C, and then after some time I just connect it to another capacitor C. We just saw that the initial final voltage it comes to is, you can treat them as a single capacitor with half a volt. Now what was the energy initially? The energy is half C into 1 square, right? This you already know, the energy stored in a capacitor is half CV square, which was actually C by 2 joules. Now once after charge sharing has taken place, in this case it is half into 2C into half square. The voltage is half square. Now this is nothing but C by 4. So the initial energy is C by 2, the final energy is C by 4. Now what happened to the remaining C by 4 of energy? Now many textbooks even get this wrong. We'll discuss this. It's a very interesting and a very simple result. We'll discuss this in the upcoming lectures. Okay. So this lecture is mainly about introducing to capacitors, a simple charge analysis, and very simple relationship between the current and voltage of a capacitor is just covered in detail here. So for different kinds of current inputs, we saw how do you get outputs across the capacitor, and for different kinds of voltage inputs, we saw how the capacitor current changes. Okay. So I'll stop at this point.